Now we have talked about various aspects like histogram equalization, etc. So we're discussing the histogram. Let us see the histogram matching. Histogram matching, also known as histogram specification. It generates a processed image that has a specified histogram. Let us assume that we have PRR and PZZ. They denote the continuous PDFs, that is probability distribution function, of the variables R and Z. This PZZ is the specified probability density function. Let S be the certain random variable with probability S is equal to TR, and we know that how to do it. We have already done in the previous section. So if certain transformation has to be applied on R to get S, we apply it like this: 0 to R PRW with respect to DW, and we go from 0 to R. And we can define a random variable Z with a certain probability. Now we take GZ, which is not from 0 to R but 0 to Z. 0 to Z. Now we have PZ, and this is say a function of T dt, and we get S. So this S is equal to TR is now L minus 1 as in the earlier case. I'm just redefining it: 0 to R PR W dW, and GZ will be L minus 1. 0 to Z PZ T dt is equal to S. Don't worry about if you are not understanding the mathematics. We'll take an example also. So what about the G inverse X? If you apply G inverse X, if I take it here and say G inverse, I'll get Z. So G inverse S is Z, that is I perform G inverse on TR, and S is nothing but transformation. After transformation which is done on R, that is our image, we get the transformed or transform image. So what is the procedure of histogram matching? First we obtain the PRR from the input image and then obtain the value of S. How? S is obtained, this is the formula which we have been using, or this is the expression which we are using. So we use the specified probability distribution function and obtain the transformation function GZ. How? GZ is known as L minus 1, now 0 to Z, not 0 to R but 0 to Z PZ T dt, that will be S. Then we map from S to Z. Why we have taken inverse? Because we want to map it from S to Z. Let us make it clear by an example. Just assume continuous intensity function. Suppose that an image has intensity probability distribution function like this. PRR is 2R by L minus 1 to the power whole square. If R lies between 0 to L minus 1, I'm just saying that if you have a 8-bit image, normally it is we have 8-bit images only, so it goes from 0 to 255. So this value probability will be 2R by L minus 1 whole square for all those values which lie between 0 to L minus 1, otherwise we'll take it as 0. And we find the transformation function that will produce an image whose intensity PDF will be like this. PZZ would be 3Z square by L minus 1 whole cube, where Z lies between again 0 to 255 for example. Otherwise we take it as 0. Then we find the histogram equalization transformation for the input image, and you know by now how we do the histogram equalization. That is S equal to TR would be L minus 1 0 to R PR W dW, that will be L minus 1, and this will be written as, because we are placing 2W by L minus 1 whole square in this place, that will be nothing but, these are constants, you just take out L minus 1 will be cancelled, and this W will be W square by 2 will get cancelled, so it will only be R square from integral 0 to R, that will be R square by L minus 1. And we find the histogram equalization transformation for the specified histogram also, because we have just known that the inverse was, or this other function was 3t square by L minus 1 whole cube. So we can write in this case PZ T dt for GZ 3t square by L minus 1 whole cube. Again we are integrating it. We know the L minus 1 cube, these are constant, we can take it out, and t square will be t cube by 3 will get cancelled, so it will be set S again. So the transformation function is something like this. We have Z is equal to L minus 1 whole square S 1 to the power 3. That is, if we replace S, which we have got as Z cube by L minus 1 whole square. So what we have got is, that is R, if we place R here, so it will be R square, this one, it will be R square by L minus 1, that will be 1 by 3. So you get L minus 1 into R square to the power 1 by 3, that is cube root. What about the discrete cases? Discrete case means it is not continuous. We are taking some discrete cases. For that we cannot use integration. We'll use sigma. We use sigma, that is discrete value addition we use. So we obtain PRRJ for the input image and then obtain the value of SK. We round the value of the integer value 0 to L minus 1. From 0 to L minus 1. We try to round it between say 0 to 255. So Sk will equal to TRK, and we know that what it suggests. It suggests that L minus 1 into this sigma of 0 to K PRRG, this one. We obtain this. This is nothing but we take L minus 1 and PRRJ is nothing but Nj by M into N. We replace it here, M by N comes out. So it will be just summation of Nj, number of time it has happened. So we use this specified PDF and obtain the transformation function GZQ and round the value to the integer 0 to L minus 1. That is GZQ will be equal to L minus 1, I from 0 to Q, and PZ is ZI, that is equal to SK. And we map SK to ZQ. ZQ will be equal to G inverse SK. Again, if you are not getting this, don't worry. We'll be taking an example. This is an example for you. So let us see how histogram matching is done. Suppose you have a 3-bit image where L equal to 8. What it means is 2 to the power 3 is 8. So you have 8 levels. Normally, in general sense, we have say 255, 0 to 255 range. So 256 is there. So normally 8-bit images give us 255, but we'll take an example from say 0 to 7. So the pixel values are from 0 to 7. Understand that pixel values are from 0 to 7 only. And the number of times those pixels they are found in an image are this. For example, if I just make a subset of image, and if I say that I have say 4 here, here and here. So how many times this 4 is there? It is 3 times. So the 3 times this is 3. This is just giving an example. This is a subset. So number of times this 4 is appearing in the whole image is 329 times. So what this is, these are the pixel values 0 to 7. These are the number of times these pixel values are appearing in the image. Then we find the PRRK, that is nothing but the number of K, that is NK, divided by 4096. So 790 divided by 4096, and that will give us 0.19. 1024 divided by 4096, that will give us 0.25. And as we know that by histogram equalization, what we have done, we will do exactly the similar way in histogram matching also. So this 0.19 will be multiplied by the highest value, that is 7, and we'll represent it. Whatever we represent, we'll take the closest RK value. For example, I'll just give you an example that just consider this 0.19. 0.19 means 0.19. And if it is multiplied by 7, what it gives? It will give you 1.33. So this will be 1.33 here, right? 1.33. So now this is 1.33. We'll take 1 as this value. So it will be 1, right? You understood? Let me give you another example, because now others will be computed by cumulative frequency. Now this 0.19 will be added with 0.25. That is 0.19, 0.19 plus your 0.25, 0.25, and that will give you 0. Let me add it for you. Just to give you one example, 0.25, because we are doing cumulatively. Okay, so that will be 4, and this is 4, 0.44. So that will be 0.44, and then we multiply this 0.44. Now we will not multiply 0.25 by 7, but you will multiply first add 0.19 and 0.25. That will come to 0.44, and then you will multiply it by 7. So it will be 0.44 into 7, and that will give you the value as 3.08. This will come as 3.08. Now 3.08 is closer to which value? It will be 3. So this will be assigned. So 3. Now this one was assigned as 1. This will be assigned as 3. And likewise, you will add these 3 multiply for this. You will add these 3 multiplied by 7, and then take the nearest value. Again, you combine these 4, then multiply by 7 and take the nearest value. Okay, I hope you understand. After this, we have to match it, this particular left one with the right one. So this is the pre-specified these number of these values are given. So this PRRK, which was from our initial image, this is the already known image whose values are already computed. So you will do exactly the same what we have done. 0.00, that is 0.00 into 7. What it will be? It will be 0 into 7, 0 into 7, 0. But now here we add, because we have added these 2 for this, it will be 0. We added these 3 for this, again 0. But we add now this 0.00 plus 0.00 plus 0.00 plus 0.15. That will come to 0.15. And now 0.15 will be multiplied by 7. So what it will be? 0.15 multiplied by 7, and that will be your 1.05. That will come to be 1.05. And now see the nearest one, which is this 1. So we will assign 0 here, 0 here, 0 here, 0 here, 0, 0, 0, and then now the fourth one will assign 1. Let me take one more example. Now we have to add all these 5 values for this one. So 0 plus 0 plus 0 plus 0.15 plus 0.20. So it will be 0.35, these added into 7. What it will be? It will be 0.35 and into 7. That value will be 2.45. 2.45. So we'll match it with 2. Okay. So all these will be 0, 0, 0, 1 and 2, and likewise. You'll add all these and then take a value. I hope you understand. So finally you'll get some certain values 1, 2, 4, 5, 6, 1, 2, 0, 0, 0, 1, 2. So you have to get this value. Let me show you here. First, we have found the scale histogram equalized value for this left one, that came to be 1, 3, 5 and 6 and 7 and 7 and 7. 7, 7. Okay, these are our 1, 2, 3, 4, 5, 6, 7, 8 values. We want 8 values. What about this? Exactly same has to be done for this only. First you have to take cumulative value, that is this sigma represent, and then you have to multiply it by 7, as I just suggested in the previous. What you are doing here is shown by this formula. Similar, exactly similar what you have done here has to be done for this also. So what the value will be? It will be this 0, 0, 1.05. We have just computed 1.05 and 2.45, and others value are here. Now we match it with these values, nearest value. So what it will be? The final value will be 0, 1, 5, 0, sorry, 0, 0, 0, 0, 0, 0, 1, 2, 5, 6, and finally 7. So we have these two values. Okay, this one and this one. These two are now matched. How they are matched? First let me write. Okay, this has to be done like this. 1, 2, 3, 4, 5, 6, 7, and one more. So 0, 1, 2, 3, 4, 5, 6, 7. What these values are coming? They are coming as 0, and then 0 and 0, then 1, then 2, then 5, then 6, then 7. So how many zeros are there? First see how many zeros are there. There are 3 zeros. So we'll take the 0 value here, all these values which are matching here, and we add the pixel values, right? Because these are discrete values, so I'll not be able to tell you how to add, because if, for example, this would have come as 2, this would have come as 2, so we will add these two values, means whichever it is corresponding to, we'll add these two values, say 66, 56 plus 329, like this. So this is how we match from one point, this histogram to another. This is your way. So histogram of a 3-bit image which is specified is given like this. Okay. Transformation function obtained from the specified histogram is like this, and this is the result of performing histogram specification compared to your this and this. And the obtained the value which we have obtained, which was this, which this went to S0, S2, S3, S4, S5, S6. These all will be, this will match to 7. Okay, like this. 1 will match to 3, 3 will match to 4, 5 will match to 5, 6 will match to 6, and 7 will match to 7. So the initial values which were there, that is 0 to 7, they are matching like this: 0 to 1, 0 to 1, 1 to 3, 2 to 5, 3 to 6, 4 to 5, and all these 5, 6, 7 will be, all these 4, 5, 6, 7 all will be matching to your 7. Okay, then finally what we are going to do is we are matching RK to ZK. 0 to 3, 1 to 4, 2 to 5, 3 to 6, 4 to 7, 5 to 6, 6 to 7, and 7 to 7. This is the example of histogram matching example. This is the image of the Mars moon, which is taken by NASA, and this one is the histogram, right? Now what we do here is, this is the transformation function of for the histogram equalization, and this is the histogram equalized image. This is the specified histogram. This one is the transformations which are applied, and now we have a enhanced image using mapping from curve, which is here. So this is the example of histogram matching, how you get a very good picture out of it. Now we also have local histogram processing. In this local histogram processing, we define a neighborhood and moves its center from pixel to pixel. So at each location, the histogram of the points in the neighborhood is computed. Either histogram equalization or histogram specification transformation function is obtained, and we map the intensity of the central pixel in the neighborhood. And we move to the next location, we repeat these procedure again. Let us take an example. This is your original image. Now this is the result of global histogram equalization. And this is the result of local histogram equalization, which is applied to this and using a 3x3 size of your kernel, you can say. Using histogram statistics also, you can do certain image enhancement. For example, you are aware of this RIPI from which we take it as M from I to 0 to L minus 1. And this U and R will be given by Ri minus M to the power N PRI on this. And sigma square will be nothing but 0 to 0, this U2, UN is this, so we take U2R for sigma square. We replace N by 2, N by 2 here. So that will be this expression. This is the average intensity, this is the variance, sigma square. And this gives us, this one gives us 1 by Mn, sigma from 0 to M minus 1 by 0 to N minus 1, Fxy. And this gives us 1 by Mn, and 0 to M minus 1, 0 to N minus 1, Fxy minus M square, Fxy minus M square. Okay, this is the variance. So this is the local average intensity, where this Sxy is nothing but the neighborhood. So we apply Ri, not this, but neighborhood on the Ri. And the local variance will be Ri minus Mxy and Pxy. This is the histogram statistics for image enhancement. First image is the image of the tungsten filament, which is magnified. And this is the result of global histogram equalization. And this one is the image enhanced using local histogram statistics. Now we come to the spatial filtering. What is spatial filtering? A spatial filter consists of a neighborhood and certain predefined operation. A neighborhood and certain predefined operation. Linear spatial filtering of say size m by n with a filter size m by n. Okay, we give expression like this. We apply WST with Fx plus S and Y plus T, where S starts from minus A to A, as T starts from minus B to B, and this is the transform image. So this is the filter mask we apply, and this filter mask which is applied on the whole image has certain weight. See, these are weight minus this. These are the positions. If this is W00, that these are the respective positions. The weight will be reflected here after performing the weight operation. And these are the pixels of image section under filter, which is this one, which has come from this part. Then the spatial correlation, the correlation of a filter WXY of size m by n with an image say Fxy is denoted by WXY star Fxy. What it says is the spatial correlation. This is nothing but minus A to A, minus B to B, WST, Fx plus S, Y plus T. The convolution, on the other hand, of a filter WXY, which is applied on Fxy, this WXY is of size m by n, so this is of size m by n, small m by n, and this is given by a convolution, a star, a filled star, it will be given by minus A to A, minus B to B, WXST, and X minus N, F, and Y minus T of F. So how we are going to do is, this is the origin, and say this is WXY. So just pad it, because if we want to apply, we have to do it for each and every row. We have to pad it. Otherwise, once this is done, this image this point will be taken care. When this will be done, this point will be taken care. When this will be done, this point will be taken care. What about these boundary points? So for boundary points, you have to add, or certain padding has to be done. Now you start. You apply this kernels, you can say, on this. Okay, initial position of W is like this. Then the full correlation result after performing all these will be something like this, because we are interested in this part only. This is the crop correlation. We can crop all these which we have padded, and this is the rotated W. You can just, this was what, WXY, you can rotate WXY also and then also apply. Again, full convolution result will be like this. So we have cropped it. We are interested in this part only. So this is the, there are certain correlation, middle row, and convolution of a 2D filter with a 2D discrete unit impulse. And these zeros are shown in gray to just simplify the visual analysis. Then we come to the smoothing spatial filters. Smoothing filters are used for blurring and for noise reduction. For blurring and noise reduction, smoothing. Blurring is used in removal of small details and bridging of small gaps in linear or curves. So if some break of curve is there, it can be made good by blurring. So smoothing spatial filters include linear filters and non-linear filters also. Smoothing. This is the spatial smoothing linear filter. The general implementation of filtering of m by n image with say weighted averaging filter of size small m by small n is given by this whole by this one. So m is given by 2a plus 1 and n is given by 2b plus 1, and we perform it like this. We will take an example also. These are the two smooth averaging filter masks. These are your values and they are multiplied by 1 by 9. So these are two 3 by 3 smoothing or averaging filter masks. These are the values which you give. These are the weights. The constant multiplier in the front is 1 by 9 and 1 by 16 is equal to 1 divided by the sum. If you sum it, it will be 9. It's 1 by 9. If you sum it, it will be 16. So 1 by 16, as it is required to compute the average. Now you see the result. This is the original image, and these are the image of smoothing when we take filter of 3 by 3 size, then 5 by 5 size like this, and this black square, as you can see at the top area of size 3, 5, 9 pixels respectively, their borders are 25 pixels apart. The letter at the bottom range in size from 10 to 24 pixels, an increment of 2 points. So the large letter at the top is 60 points. The vertical bars are 5 pixels wide and 100 pixels high. So this separation is 20 pixels. So the diameter of the circle is 25 pixels and their borders are 15 pixels apart. And their intensity levels range from 0 to 100%. Black in increments of 20%. And the background of the image is 10% black. The noisy rectangle area of 150 by 120 pixels. This is the gross representation of objects. This is the image of size say 528 by 485. Now this is the image filter with a 15 by 15 averaging mask. Okay, and this is the result of thresholding. You can threshold it. Then we have non-linear filters, that is order statistic filters, non-linear filters. So these are based on ordering or ranking of pixel contained in the filter mask, and we replace the value of the center pixel with the value determined by the ranking result. For example, median filter, Maxim filter, min filter, all these are non-linear order statistic filters. We apply the median filter for noise reduction. This is the X-ray image of a circuit board with certain salt and pepper noise, as you can see. And this is the noise reduction with a 3 by 3 averaging mask. And this is the noise reduction with a 3 by 3 median filter. This is averaging mask and this is by median filter. See how clear it is. So this was again some more aspect of your transformation and intensity processing. Thank you so much. We'll be taking one more of this.